This is Math 105, Section 2.5a. We're talking about how we can transform graphs by shifting vertically or horizontally, reflecting, or shifting across the x or y axis. So let's look first at vertical shifting. We vertical shift a graph. So if you take a function like f of x, okay, and you add a constant to it, where let's c be a positive number. So we add a constant number to it. What we're doing is we're shifting the graph c units up. Okay, so f of x plus c would go c units up, and then if we take our function and subtract c, whatever c is, let's say is 2, then we would move our graph down by that much. Okay. So the y-coordinate of each point on the graph of y equals f of x plus c is c units above the y-coordinate of the corresponding point on the graph of y equals f of x. So it's going to be c higher. Okay, so this we would shift up by c, and this one we would shift down by c. And the vertical shifts are pretty easy to see when you look at them. When you take like x squared and make it x squared plus 2, you move x squared up 2. Okay, so we get the graph of y equals f of x plus c by shifting the graph of y equals f of x upwards c units. Okay, and we can see that here, that this is f of x is that blue one, and then y equals f of x plus c is the red one, and everything's moved, shifted up by c. Okay, so to graph y equals f of x plus c, shift the graph of y equals f of x upwards c units. Okay, and then similarly for a downward shift, we're going to subtract the c. So we get the graph of y equals f of x minus c by shifting the graph of y equals f of x downward c units. Okay. So that's this scenario. We start with our blue graph, y equals f of x, and then y equals f of x minus c is shifting everything down by c. Okay. Same shape of the graph and everything else. Okay, so let's start with f of x equals x squared, and we want to look at how we move that to get g of x equals x squared plus 3, or for part B, h of x equals x squared minus 2. Okay, so you can see x squared is the blue one here. Okay, and then x squared plus 3 is we just move everything up 3 units, every point up 3 units, so we get this red one. And then x squared minus 2, h of x, would be moving the blue one down by 2 everything. Okay, so that would be the purple. Okay, and again, there's arrows here at the end of each of these curves on both sides. Okay. Horizontal shifting is a little more subtle. I mean, you got to think about this a little more. So when we shift it c to the left, let me write that down. This is c to the left, would be this side. Okay. And this would be c to the right. Okay. And then notice we have, for the left, we're taking x and instead putting x plus c in our function instead of x. And here we're putting x minus c in our function instead of x. So it's a little bit different. It's kind of a little bit counterintuitive, but it's also tricky because we have to figure out what are we doing when we're putting x plus c in our function instead of x, and what are we doing when we put x minus c in our function instead of x. It's not always obvious. Okay, so this when we change f of x to f of x plus c, we're moving it c to the left, and we change it to f of x minus c, we move it c to the right. Okay, and then again, c is positive. Okay. Since x minus c is c units to the left of f of x, it follows that the graph of y equals f of x minus c is just the graph of y equals f of x shifted to the right c units. And similar reasoning shows that the graph of y equals f of x plus c is the graph of y of f of x shifted to the left c units. Okay, so it's, it makes sense if you break it down, but it might seem counterintuitive at first. So, but just keep in mind that when we put x plus c in there, that's a shift left by c. When we put x minus c in our function, that's a shift right by c. Okay, so here's f of x, and is the blue one, and f of x minus c, we move it c to the right. Here, f of x is the blue one, and we put in x plus c in our function instead. We move it c units to the left. Okay. Okay, so Let's look at an example. Use the graph of f of x equals x squared to sketch the graph of each function. So we want to look at g of x equals x plus 4 squared for a, and h of x equals x minus 2 squared for b. So it's sometimes helpful if you take the x out of your function and write it with blank parentheses wherever you see the x. So we can write f of blank equals blank squared. And then you can kind of see what's happening when we get this function. What we're doing is we're putting x plus 4 in our function instead of x. See, because when you put an x plus 4 here, you get x plus 4 squared. So that would indicate that we're shifting it to the left by 4. Okay. In other words, we shift the graph of x squared to the left by 4. Okay. And then here, we're plugging in x minus 2 in our function instead of x. Okay. I think here we have x plugged in, right? So we're going to move h, this one, we're going to move x squared 2 to the right. So we can see that, the blue one is our x squared. X plus 4 squared is shifted the whole thing 4 to the left. Okay. And then h of x equals x minus 2 squared, we shift the whole blue one 2 to the right to get the purple there. Okay, for reflecting graphs, when we change y to the opposite, in other words, we change y to minus f of x instead of f of x, it's simply the negative of the y coordinate of the corresponding point on the regular graph, y equals f of x. So this is a reflection in the x-axis. Okay, so if you put in minus y for y, let me write that down. Minus y for y, that's an x-axis reflection. Okay. And then similarly, if we put in minus x instead of x in our function, so we have minus x here instead of x, so we're looking at f of minus x. So then the graph that we have is a reflection of the original graph on the y-axis. So if you have minus y for y, you're reflecting across the x-axis. And if you have minus x for x, you're reflecting across the y-axis. So minus x for x, hope I can fit it in there. Okay. That's a y-axis reflection. Okay. So think of the opposite variable in each case. If you're changing y to minus y, then you're reflecting x-axis. If you're changing x to minus x, then you're reflecting y-axis. Just like, you kind of think of, well, your intercepts. You set the opposite variable equal to 0. X-intercept set y equal to 0. Y-intercept set x equal to 0. Well, the reflections are kind of a similar idea, is that you take the opposite variable, you change the sign, opposite variable and change the sign, and that reflects across. So if you change the sign of y, you reflect across the x-axis. You change the sign of x, you reflect across the y-axis. So here's y equals f of x, whatever that curve is, the blue one. And if you change your y to minus y, so y equals minus f of x, we're changing the sign of y, then we just reflect across the x-axis, and you can see that that red one is just a reflection across the x-axis. Okay. And then if we change x to minus x in our function, so we go y equals f of x to y equals f of minus x, we go from this blue one here to this red one here, which is reflected across the y-axis. And it speaks directly to, we talked about symmetry, remember, when you said if you put in minus x into your function, you get the same y, then you have symmetry across the y-axis. If you plug in minus y and you get the same x, then you have symmetry across the x-axis. So it kind of goes, speaks directly to the symmetry that we talked about earlier. Okay, so let's look at a couple examples. First, let's look at the graph of f of x equals minus x squared. If we start with y equals x squared, the blue one here, what we're doing is we're changing the sign of y, not the sign of x. We're changing, the whole function to the opposite, right? X squared to minus x squared. So this is reflected across the x-axis because we're changing the sign of y. We're changing y to minus y, basically. So from the blue, we get the red here reflected across the x-axis, and that's now parabola opening down. Okay, and the next one we'll look at is g of x equals square root of minus x. Now, if we start with y equals square root of x, which is this blue one, remember the arrow keeps going, right? We're changing x to minus x in the function, which means we're going to take this blue and reflect it across the y-axis. So remember, we reflect across the y, we change x to minus x. So we're going to get the red one that's going like this, and that's the square root of minus x. So notice the domain for these two is, for the blue one, my domain is x is positive or 0. Remember, it can be 0. You can take the square root of 0. And then for this one, my domain is x is less than or equal to 0. Okay. Because, we're taking square root of minus x, which means x can be 0, but it can only be negative in order to get a positive here. So, see the opposite domains there. Okay, the next concept we're going to look at is vertical stretching and shrinking. So, think about like you kind of pull up on the graph or pull down on the graph to stretch it, okay, or you shrink it. Okay. So, when we do that, we're not changing x to x plus c or y to y plus c, but we're taking our function and multiplying it times some c, where c is positive. Again, so we have c is greater than 0. Okay. C is some positive constant. And then we're taking that and multiplying it times our function. So we have two cases. One case is when c is bigger than 1, like it's 1.1 or 2 or 5 or whatever, but it's bigger than 1. So when that's true, what you're doing is you're taking this is our blue graph, is that we're starting with our f of x, and you're kind of pulling it up. In other words, you're making the y values higher. You're stretching them. Now when they're 0, they don't change, right? So you can see that when y is 0, they're going to be the same. But we're kind of pulling up on the graph to stretch it vertically. Okay. And then the other case is when c is a fraction, between 0 and 1. So let's say, for example here, maybe our c could be 2 or whatever. Okay. Here our c might be 1/2. But when we multiply it times our function, we're going to get a lower y value, right? Because we're multiplying it times something between 0 and 1. So instead of stretching it, we're going to shrink it. Okay. So we go from the blue here, y equals f of x, to the red here where it shrunk. It's kind of pushing it down on it instead of pulling up on it vertically. Okay. And note again, at the zeros, it's going to be the same because 1/2 times 0 is still 0, right? And the same with 2 times 0. 2 times 0 is still 0. This might be, the c might be, it's probably not 2 here. It's probably more like 1.5 or something. But you get the idea is that we're pulling up on it, we're stretching it. Okay. When c is bigger than 1. Okay. And that comes from multiplying your function times that c in both cases. Okay. Okay, so we're going to start with x squared, and we're going to look at the graph of 3x squared. So here our c is bigger than 1. Okay. So we're going to stretch the graph of f vertically by a factor of 3. Then we're looking at 1/3 x squared. Here our c is less than 1, between 0 and 1. So we're going to shrink our graph down by a factor of 1/3. Okay. So here's our original graph is the purple one. That's x squared. Okay. And then that's f of x. And then g of x is going to be the red one. And that's stretching it because our c is bigger than 1. So we just take that purple one and stretch it, kind of pull up on it. And then 1/3 x squared, h of x, here our c is between 0 and 1. So we're going to take that purple graph and squish it down. Okay. And notice they all meet at 0, 0 because when you multiply something times 0, you still get 0. Okay. So that's vertical stretching and shrinking. Okay, I just want to talk briefly about horizontal stretching and shrinking. I actually won't. We'll look at this when we get into trig functions, but we're not going to worry too much about it now. So, but I just want to kind of show it to you. I won't test you on this. But what happens when you take x and multiply it times some c? Okay, so if you're inside your function, so if your c is bigger than 1, what you're going to do is shrink it horizontally. So you're going to kind of push it inward, left and right. Okay, see, so we start with this blue. And let's see, our c is less than 1, and we go y equals f of cx. We're going to kind of squish that curve in. Okay, and then just the opposite happens when c is a fraction. You start with the blue one here, and then when you apply a c times x in your function, you're going to stretch it out. Okay, so again, it's sort of like the horizontal shift where it's kind of counterintuitive, that when c is greater than 1, you shrink it, and when c is less than 1, you stretch it. Okay, sort of the opposite of what you'd expect. So let's look at a quick example. Let's say this is our y equals f of x, is this sort of sawtooth graph, and you can see it goes up and down at 1, and then it probably goes up and down at 2, and up and down at 3, and it goes up to 1. So it's got a cycle to it, right? And we're going to look at f of 2x and f of 1/2 x. So here's f of 2x. You can see it squishes it. So it's going to cycle twice as fast. So it's going to go up and down at half, and then up and down another half, and up and down another half instead of at 1. It still goes up to 1 now. It doesn't change the vertical, just changes the horizontal. And then if we look at f of 1/2 x, here our c is less than 1. It stretches it out. So now it goes up and down from 0 to 2 instead of from 0 to 1. Okay, and then etc. And it takes 2 to go through that cycle instead of 1 on x. Okay. Still goes up to 1 on the y, so it doesn't change the y. It's just stretching it horizontally. So you kind of think of you're stretching it or squishing it horizontally, but you're not changing the vertical at all. Okay, it still goes up as high as it did before. Okay, but I'm not going to worry too much about this. This is just wanted to show this to you. Okay, now let's talk about the concept of even and odd functions. Okay. When this is true, that f of minus x equals f of x for every x, then f is called an even function. Okay. Now think about that. When you're putting in minus x and you're getting the same y, right, you have symmetry across the y-axis. So we say an even function has symmetry across the y-axis. Okay. So we say it's symmetrical with respect to the y-axis. This is for the graph of an even function. Okay. And notice when we put in minus x, we get the same x squared. So f of minus x equals minus x squared, which is minus 1 squared times x squared, or minus x times minus x. But we still get x squared when we do that. Okay, and we can see that the even function, has that symmetry across the y-axis. Okay, so an example is f of x equals x squared is an even function. So plug in minus x for x and see if you get the same y, and that's how we determine whether we have an even function. Okay, and the next case is if we plug in minus x for x and we get the opposite y, okay, in other words, f of minus x equals minus f of plus x, then we call f an odd function, okay. So for example, f of x equals x cubed is odd because if you plug in minus x, f of minus x would be minus x cubed. What we're doing is multiplying minus x 3 times, which gives us a minus x cubed, which is minus f of x, okay. So think about that. That's symmetry about the origin, right? So when we say an odd function means so odd means we plug in minus x, get minus y. That's origin symmetry, okay? And then back to even function. So that's odd. Even, you plug in minus x and you get same y, and that's symmetry across the y-axis. Let's just kind of summarize those two. Okay, so let's look at the odd function now. Odd, plug in minus x, get minus y. So this is our odd function. You can notice we have that symmetry about the origin. Okay, so when you plug in minus x, you get the opposite y. Okay, so this is odd. F of minus x equals minus f of x. Remember, f of x is y. So think of plug in minus x and you get the opposite y. Okay. Even as you plug in minus x and you get the same y, right? Because f of x is y. So this would be symmetry across the y-axis. Okay. So this is your even case here. This is your odd case here. Okay, and it's the two types of symmetry we already talked about, right? Symmetry for functions, that we have symmetry across the y-axis or symmetry across the origin, right? Remember, we can't have symmetry across the x-axis for functions because that would be violate the vertical line test. Okay, so let's look at some examples. First one, f of x equals x to the 5th plus x. So we start by plugging in minus x into our function, and again, it's helpful to write your function like this: f of blank equals, now I'm going to put blank to the 5th plus blank. And then we're going to plug in minus x where you see the blanks, right? Which is what we're doing here. This actually is written wrong. It should be minus x to the 5th. So let me rewrite that. That should be minus x parentheses to the 5th plus minus x. Okay. So let's scratch that. Okay, so put in minus x here and here, wherever you see the parentheses. And minus x multiplied 5 times gives us minus x to the 5th, so there's going to be a negative in front. And then minus x. So you can see it's the opposite of what our original y was, because our original y is x to the 5th plus x, and we've got minus x to the 5th minus x. So we can see that this is true, that f of minus x is minus f of plus x, or f of x. Okay. So we have symmetry across the origin, so this is an odd function. So minus x to the 5th minus x is the same as minus x to the 5th plus x in parentheses. So we can see it's minus f of x. So we say f is an odd function. Okay, let's look at b. So remember, for b our function was g of x equals 1 minus x to the 4th. And again, it's helpful to take the x out and just put blank parentheses wherever you see the x. So g of blank equals 1 minus blank to the 4th. And then we're going to plug in minus x into our function instead of x. So g of minus x would be 1 minus x to the 4th. Now when you take minus x to the 4th, you're going to get plus x to the 4th because you're multiplying it an even number of times. Okay. So this minus x to the 4th, minus x in parentheses to the 4th is just x to the 4th. So this just ends up becoming the same function, 1 minus x to the 4th, because we have a minus here. So this ends up becoming g of minus x equals g of x. So this is even. So we have symmetry across the y-axis, okay, for this one. Okay. And then we had symmetry across the origin for that first one when we had that odd function, right? Or we would reflect across the origin here. We'd reflect across the y-axis here. Okay, and that last example we're looking at is h of x equals 2x minus x squared. Okay, and we're going to plug in minus x for h. So again, take the x out and put blank parentheses as a guide. So we're going to put minus x here, here, and here, and that gives us h of minus x equals 2 times minus x minus x squared. Okay. And we take minus x squared, we get plus x squared. So this thing would be plus x squared, and we're taking minus 2x minus x squared. Now notice this is not the same as h of x, but it's not the opposite either, right? Because notice the minus x squared is the same here, but the 2x changes sign. So h of minus x is not equal to h of x, and h of minus x is not equal to the opposite of h of x. So we say that it's neither even nor odd. It doesn't have symmetry across the y-axis or the origin. Okay. So in this case, because it doesn't change the function completely to the opposite, or it doesn't keep it the same, we don't have either one of those reflections across the y-axis or across the origin. Okay, so just to summarize from our 3 examples, the first one was an odd function, x to the 5th plus x, and notice we have symmetry across the origin. Okay, it reflects across the origin, so we can take this part and reflect it across the origin to get that part. Okay. Part B, 1 minus x to the 4th, looks like this, but it reflects across the y-axis. We have that y-axis reflection. So we could graph part of it, half of it, like the positive half, and reflect it. Okay. And then part C, it does have symmetry, but it's not across the y-axis or the origin. It's actually symmetrical across the line x equals 1, but we won't worry about that symmetry. But notice it doesn't have either symmetry. It's neither odd nor even, so it doesn't reflect across the x-axis. Sorry, it doesn't reflect across the y-axis, or it doesn't reflect across the origin either. Okay, so that's it for section 2.5. We'll look at some examples in class. I'll probably use a graphing application just for ease of visualization on the overhead. So we'll look at some more examples of that in class.